Hello everyone, welcome to MrMiers Math Channel. Today we're going to start chapter 13 and we're going to begin by talking about the midpoint formula, distance formula, and parabolas. This is all going to be review from what we've done previously, but it's a good starting point in getting into chapter 13. So the goal of the lesson will be to be able to use the midpoint and distance formula and also to be able to graph parabolas. Alright, so let's get into it. To start, we're going to talk about midpoint formula. So the midpoint formula is a way that we can find what's in the middle of 2 points on the coordinate plane. All right, how we can find what's in the middle is just by taking the average. All right, so you'll see on the left we have the average of the x-coordinates of these 2 points on the coordinate plane, which would be x sub 2 plus x sub 1 divided by 2. And then on the right, we see the average of the y-coordinates, which is y sub 2 plus y sub 1 divided by 2. All right, so by finding the average, we can figure out what's in the middle of those 2 points. Moving on to example 1, we're going to find the midpoint given these 2 endpoints in each example. All right, so in example A, we've got 2 points here. One we could call point 1, in which we could write down x sub 1, y sub 1. Remember, these subscripts just means that these 2 coordinates go together to form a point that's on our graph. And then here we have the second point, so we could call that x sub 2, y sub 2. We're going to average the x coordinates first, so -1 plus a -1 divided by 2. And then we're going to average the y coordinates, so 10 plus a -4 divided by 2. All right, -1 plus -1 is a -2. -2 divided by 2 is -1. And then for the y coordinate, 10 plus -4 is 6. 6 divided by 2 is 3. So here we have what's in the middle of these 2 points, all right, by finding the average. If we take a look at part B, we're going to do the same thing. All right, 0 plus -4 divided by 2, -10 plus -1 divided by 2. -4 over 2 would be -2, so that would be our x-coordinate for the midpoint. And then -10 plus -1 is -11, and then divided by 2 we could just write as -11 halves or -5.5. All right, oftentimes you'll see that I will write down x sub m and y sub m. And when I do that, I mean the x-coordinate of the midpoint and the y-coordinate of the midpoint. And also there's another way that we could find the midpoint that I find to be maybe a little bit easier. If we want to find what's in the middle of these 2 points, we could just figure out what is in the middle of -6 and 9 and what's in the middle of 3 and -2. And we could just think about this in terms of a line. All right, so if this value is -6, then we got -3, 0, 3, 6, and then 9. And we're just trying to figure out what is exactly in the middle. So we can just figure out, go end to end, and then what we find is what's in the middle is going to be exactly in between 0 and 3, which would be 1.5. So that's another way that we could figure out what the midpoint of those, or what that middle value of the x-coordinates is. And then same thing for the y-coordinate. All right, from 3 to -2, all we have to do is just figure out what is in the middle of that. And I'm just going to go up by 2's here. So -2, and then I'll get all the way up to 4. So we have -2 and we have 3. We're just trying to find the middle. All right, so we're going to go 2 units at a time. And then from here, we're at 1 and 0. What's in between 1 and 0? 0.5, or 1/2. All right, that's another way graphically that we could go about finding the midpoint. All right, for the last one, let's just use the formula. So we have 10 plus 2 divided by 2, and then -3 plus -4 divided by 2. 10 plus 2 is 12. 12 over 2 is 6. -3 plus -4 is -7. -7 over 2 is a -7 halves, or -3.5. All right, awesome sauce. Now we're going to move on to the distance formula. All right, so to find the distance between 2 points on the coordinate plane, we could use the distance formula, which is really just Pythagorean theorem. All right, we're just finding the hypotenuse, essentially, of that right triangle that's formed. If x sub 1, if x sub 1, y sub 1 is here on our graph, x sub 2, y sub 2 is here on our graph, we are just finding that hypotenuse of that right triangle, and we're just calling that d for distance. All right, so now let's use this. All right, so we can call the first point x sub 1, y sub 1. We could call that second point x sub 2, y sub 2. And just as a side note, it doesn't really matter what point you call x sub 1, y sub 1, and what point you call x sub 2, y sub 2. Just pick a point, call that first point x sub 1, y sub 1. Pick another point, call that second point x sub 2, y sub 2. All right, then from there, we're just going to plug this into the distance formula. We have x sub 2 minus x sub 1, which would be negative 6 minus 8 squared. And then we have y sub 2 minus y sub 1, negative 7 minus 3 squared. And now let's simplify. Negative 6 minus 8 is negative 14. And we're going to be squaring that value. Whoops. I don't know why I wrote negative 144. Let me go back. And then negative 7 minus 3 is negative 10. And we're going to square that value. All right, so 14 squared, that's 196. 10 squared, that's 100. So we have the square root of 296. And for these, we're just going to round this to the nearest hundredth. All right, so if we round this to the nearest hundredth, we have 17.20. All right, so that would be the approximate distance between those 2 points on the coordinate plane. Now, just like with midpoint formula, we have another way that we could do this, and I'm thinking more graphically here for the second example. Instead of using the formula, all we really need to do, since what we need to find is that hypotenuse of the right triangle, is we just have to know what is the difference between the x values to get that side length, and then what's the difference between the y values to get that side length. So I'm just going to take a look at these x values first. The distance between negative 5 and 6 on the coordinate plane would be 11 units. And now we're negating the need to use negative numbers here. All right, all we have to do is use positive numbers. So we don't have to worry about any sign errors that might occur if we forget parentheses or whatnot here. All right, then in terms of the y values, from negative 1 to 4, that's 5 units. So now when actually computing the distance, we're basically skipping this first step, the step of setting it up and getting right to finding the distance. We have one side length, another side length, so the distance is going to be the square root of the quantity 11 squared plus 5 squared. All right, this is a little bit easier, a little bit quicker in finding the distance. All right, so we would have 11 squared plus 5 squared, that's 121 plus 25, it's 146. If we round it to the nearest hundredth, we get 12.08. All right, so we could do it either way in both of those examples for midpoints and for distances. We could use, the more algebraic method, or we could use the more geometric method in finding the midpoint and the distance. All right, getting on to example 3. Let me clear the board here. We got 2 more examples. I'm just going to straightforward use that little shortcut using the graphical features that I know. All right, the x-coordinate is 3 units away. So we'd have the square root of the quantity 3 squared plus the difference between the y values, which would be another 3 units between negative 4 and negative 1. So we have 3 squared plus 3 squared, and we get 18. This time we're going to simplify using our radicals. So we have to write this in simplified radical form. Now if we forget, we could always use that factor tree and take out our lowest primes. circle our pair, and we've got 3 root 2. All right, otherwise, we're taking out the biggest perfect square, and that's also an easy method to simplify our radicals. All right, for part B, let's do the same thing. The distance between the x values would be 3 units. The distance between the y values would be 5 units. 3 squared plus 5 squared is root 34, the square root of 34. And then in terms of the square root of 34, we can make a factor tree, but one thing that we'll notice is we take out a 2, we get 17, and both of these are prime, so we don't get anywhere. So the simplified radical form for that is root 34. All right, on to the last part, which is talking about parabolas. We're going to graph the equation in vertex form. It says the quantity x minus 3 squared plus 2. Now, we've talked about parabolas before, so I'm going to be skipping a little bit here. In terms of the direction of opening, that's dependent on the a value, which is right here before the parentheses in vertex form. And right here it's implied. It's implied to be 1. Now 1's a positive number, so that means the direction of opening is going to be up. It's going to look something like this. And then the vertex is located right here. Right, here's vertex form. Oops. We have y equals a times the quantity x minus h squared plus k. So h is actually positive 3. So what we're subtracting from x here. And then k is positive 2. And then finally, for the axis of symmetry, that's just where the x value is at. Okay, that's just going to be that line of symmetry there running through our graph. So with these things, we can start to graph this function. So the vertex is 3, 2, so I'm going to graph that point. Okay, the axis of symmetry is x equals 3, so I'll do that in a different color. That's just that vertical line running through that point. So it should be symmetric on both sides of the graph there. Now we need some points. So we could set up a table to figure out some points, and my recommendation would be let's put the vertex right in the middle. All right, and then we can go up and down in terms of the x value and plug in those values into the function to get our output values. So I'm just going to choose 2 and 1 and 4 and 5 for this first example. So let's plug in 2. We'd have 2 minus 2 squared plus 2. 2 minus 2 squared, 2 minus 3 squared would be negative 1. Negative 1 squared is 1, so that's just 1 plus 2, or 3. We should have some symmetry, so that same value on the other side, same distance away from our vertex, should be the same. So we're expecting 3 here. And if we plug it in, we should get it. 4 minus 3 is 1, 1 squared is 1, and 1 plus 2 is 3. Now if we plug in 1, we have 1 minus 3, which is negative 2. Negative 2 squared is 4. And then 4 plus 2 would be 6. Now once again, we expect symmetry, so we should get a 6 over here. And let's just evaluate and double check that that's true. 5 minus 3 is 2. 2 squared is 4. So we have 4 plus 2, which is 6. Awesome. So we see that symmetry. Let's graph those points so we can see it graphically. So 2, 3 is one of those points. 1, 6 is another one. 4, 3, and 5, 6 are the other 2 points. Ooh, a little rough sketching here. But when we graph those points and draw our parabola that's facing up, we see that symmetry in the graph as well. Awesome. All right, let's go on to the next one. So in example 5, we're going to take some shortcuts here and just use some of the patterns that we've seen before in parabolas to do this a little bit more quickly. All right, so once again, we still start in the same place. We got to figure out the direction of opening. So A is negative 1 in this example, and since it's negative, the direction is going to be down. So we're going to have like an upside down parabola, kind of looks like a hill. Okay, a hill has a peak. All right, and that peak of the hill is going to be our vertex. So our vertex is going to be the point 5, 2. Notice it might be a little confusing in terms of the x value. The x value is going to be the opposite sign of what you see in here. All right, the x value is what we're subtracting from x, and what we're actually subtracting from x is 5. Okay, then the axis of symmetry is going to run right through that x value, so that's going to be the line x equals 5. All right, so let's just begin by drawing the vertex and the axis of symmetry here. So the vertex is 5, 2, and then the axis of symmetry is that vertical line x equals 5. All right, note that it's a dotted line. That line is not actually a part of our graph, so that's why it's not a solid line here. A solid line indicates that each one of those points on that solid line is a part of our graph. So since this isn't a part of our graph, it's a dotted line. Now another thing that we could do to get these other points that are on our graph is that we could use some of the patterns that we've learned before. All right, I'm still going to draw this table, and I'm going to write the point 5, 2 right in the middle, and then just write down some other values that we could use. But we're going to use some patterns here to figure out these y values. Now, in a typical quadratic where a equals 1, the pattern of increase is like so. That increase gets larger every single time. So we start by going up by 1, then we go up by 3, 5, and 7. If that a value is different, then we just multiply that a value by each of these. So if a was 2, at the very start, when we go up by 1 in terms of x, we'd go up by 2 in terms of y. Then 2 times 3 would be 6. Then 2 times 5 would be 10. Then 2 times 7 would be 14. That's just the pattern that is that quadratic nature. So in terms of this one, we have a equaling -1. So since a equals -1, it's actually going to go down by 1. So on both sides, we're going to go down by 1. Then we're going to go down by 3 from here. So we'd get -2 and -2. Then we're going to go down by 5. So we'd get -7 and -7. All right, otherwise, of course, we could find those output values by just plugging in these values of x. Now let's plot those values. And here we get our downward facing parabola. All right, folks, that's it. If you found this helpful or enjoyed the content, like, subscribe, and share. Thank you all and have a good day.